Greetings, my dear listeners. Today we set out on a journey that both excites the imagination and challenges the mind. Could black holes be portals for travel? In other words, is it possible that in the very depths of the cosmos lie gateways to other worlds, wormholes? At first glance, this sounds like the plot of a science fiction novel. And indeed, the image of a tunnel in space-time connecting distant points of the universe or even different universes has long been part of culture. But few realize that this idea has serious roots in physics. Let us begin with Albert Einstein himself, who together with Nathan Rosen in 1935 proposed the concept of bridges in space-time, later called Einstein-Rosen wormholes. Their calculations showed that the equations of general relativity allow such tunnels to exist. In theory, they could connect two distant regions of space. But there was an immediate problem. Such bridges, according to the math, would be extremely unstable and collapse instantly. This gives us the first important thought. Mathematics itself permits the possibility of portals. The question is whether nature can realize them. In culture, wormholes have long been symbols of hope and mystery. Think of films like *Interstellar* or *Contact*. In them, wormholes become roads to distant worlds, symbols of overcoming boundaries. But what does science say? Here we encounter two levels of reflection. The first is purely scientific. Are such tunnels really possible, and under what conditions might they exist? The second is philosophical. What does the idea of a shortcut to other worlds mean for us? From a physics perspective, the main difficulty lies in keeping a wormhole open. For this, calculations show, one would need a special kind of matter, so-called exotic matter, with negative energy. Under normal circumstances, we do not encounter such matter, but quantum theory allows for effects in which energy can take negative values. One example is the Casimir effect, where vacuum fluctuations between two close plates create unusual pressure. These quantum hints suggest that the bizarre requirements might not be entirely beyond reach. Philosophically, the very possibility of wormholes raises astonishing questions. If we could move through space instantly, how would it change our sense of distance and time? What would happen to our feeling of home if, at any moment, we could be millions of light years away? And deeper still, if wormholes connect different universes, does that mean our reality is only one among countless others? The history of science shows us that ideas once dismissed as fantasies sometimes become real. Remember that atoms were once only a philosophical speculation, yet today our entire technology rests upon them. So why should wormholes not someday emerge from imagination into reality? For now they remain a hypothesis. We have not discovered a single piece of direct evidence for their existence, but the very possibility that such portals might hide within black holes inspires both scientists and dreamers. In the chapters to come, we will explore in detail how black holes and wormholes are connected, why physicists search for portals in their depths, and what obstacles stand in the way of this enthralling idea. When we speak of wormholes, the question inevitably arises, how are they connected to black holes? For it is black holes that are often considered candidates for gateways to other worlds. Let us recall, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape it. At its center lies what theory calls a singularity, a point where the familiar laws of physics break down. At first glance, this seems like the ultimate end, but in Einstein's equations, one can find hints that a singularity may not only be an end, but the beginning of something new. In the 1960s, physicists studied the solutions of general relativity and discovered intriguing features. One such solution, an extension of the Schwarzschild metric, showed that it is mathematically possible to describe two connected regions of space-time. Between them exists a bridge resembling a wormhole. This bridge came to be called the Einstein-Rosen bridge. Yet this beautiful idea has a problem. Such bridges are highly unstable. The slightest disturbance causes them to collapse. Imagine building a tunnel out of sand. A single touch is enough for it to cave in. So it is with Einstein-Rosen bridges. Their existence seems confined to mathematical abstraction. And yet the link between black holes and the idea of wormholes continues to captivate the imagination. Could it be that within the depths of a black hole lies an exit to another world? Could singularities themselves be gateways? Here another concept arises, that of white holes. If a black hole swallows everything that falls in, then a white hole, in theory, does the opposite. It spews out matter and energy, refusing entry to anything. In some models, a wormhole connects a black hole to a white hole. Enter one, emerge from the other. It sounds like a myth or legend, yet the equations allow it. Philosophically, this is striking. Where we are accustomed to seeing only an end, science suggests imagining a beginning. Where everything vanishes, a new world may arise. And this image reflects the very spirit of science, to seek paths where only dead ends appear. Of course, for now, these remain hypotheses. We have never observed white holes nor stable wormholes, yet the notion that black holes might be portals to other universes remains one of the most enthralling in astrophysics. In the chapters to come, we will discuss what conditions are required for a wormhole to be stable and traversable, and whether it might ever be possible to pass through such a cosmic gateway. Now that we have seen how Einstein-Rosen bridges appear in Einstein's equations, and why they are so unstable, we must ask the next question. What would be required for a wormhole to be suitable for travel? This is an important point. In scientific literature, such wormholes are called traversable. Their key feature is that they must remain open long enough for at least a light signal to pass through, and ideally, a spacecraft. Calculations show that to prevent the throat of a wormhole from collapsing, one would need so-called exotic matter. This matter must have negative energy density, meaning it behaves in the opposite way to ordinary matter. Ordinary matter creates gravity that pulls everything inward. Exotic matter, by contrast, must repel, providing support for the tunnel. But does such matter exist in reality? Here the debates begin. In quantum physics, there are indeed effects where energy behaves in unusual ways. One example is the Casimir effect. If two metal plates are placed extremely close together, vacuum fluctuations create a force pushing them toward one another. The energy in the system can be interpreted as negative. This does not mean we have a ready-made brace for a wormhole, but the very existence of negative energies inspires physicists. Science fiction often depicts wormholes as stable tunnels through which ships glide effortlessly. But in reality, even if exotic matter exists, the amounts required would be enormous, and controlling it would be unimaginably difficult. This is not simply an engineering challenge, but a challenge to our very understanding of matter and energy. Philosophically, this raises an intriguing paradox. To open a path to new worlds, one would need a substance that we have never seen in ordinary experience. In other words, the very possibility of travel demands stepping beyond the known. It is like a key forged from the material of another reality. Historically, the idea of traversable wormholes was actively developed in the late 20th century. Kip Thorne and his colleagues explored the possibility of such objects and even advised science fiction writers on how to describe them realistically. Thanks to this work, we received one of the most scientifically grounded depictions of a wormhole in the film Interstellar. But the question remains, even if a wormhole could exist and be traversable, would it be safe? For space is full of radiation, gravitational waves, quantum effects. Could a tunnel withstand all of these influences? In the next chapter, we will examine in detail the physical dangers of traveling through wormholes and what prevents us from imagining them as convenient cosmic highways. We already know that for a traversable wormhole to exist, exotic matter would be required. But even if we imagine such matter to be available, another question remains. How dangerous would the journey itself be? First, we must think about gravity. Near the throat of a wormhole, enormous tidal forces may arise. They can stretch and compress objects, turning them into thin threads. Scientists call this process spaghettification. If the tunnel is not stable enough, any body entering it may be torn apart before reaching the exit. Second, there is radiation. Near black holes and wormholes, space is filled with high-energy particles and radiation. For a spacecraft or even a stream of information, this could pose a serious obstacle. To make travel possible, we would need to learn how to shield ourselves from conditions that today seem utterly destructive. A third problem is quantum fluctuations. Space-time on small scales is not smooth but constantly fluctuating. These fluctuations could cause a wormhole to become unstable even with exotic matter present. And while equations may depict a wormhole neatly, real space may be far more chaotic. Philosophically, this brings us back to the question, should such portals be simple and safe? Perhaps the very idea of instant travel requires risk and courage, for if the road to other worlds were easy, it would not feel so mysterious and alluring. Interestingly, even in scientific models, wormholes are sometimes described as one-time structures. One might pass through them, but afterward they collapse. They are like doors that open only once. And here arises the question, would we dare to enter knowing there would be no return? The history of science shows that nearly every breakthrough was first seen as dangerous. When the locomotive was introduced, people feared that speeds of 40 kilometers per hour would kill a human. When airplanes were invented, they were called a mad idea. Perhaps wormholes will follow the same pattern. What seems deadly today may one day become ordinary. For now, these reflections remain in the realm of hypothesis. We do not yet know whether wormholes could ever be safe, but we do know this. The very idea continues to inspire scientists to search for new answers. In the next chapter, we will discuss how science distinguishes between closed and open wormholes and what this means for future research. In the previous chapter, we spoke of how dangerous a journey through a wormhole might be. Now let us examine an important distinction. Can wormholes be closed and open? And what does that mean for science and imagination? Closed wormholes are tunnels that exist only for a fleeting moment before collapsing. They arise spontaneously in the quantum foam, the unimaginably small scales of space and time. According to quantum theory, space itself boils like a bubbling soup, with tiny bubbles constantly forming and disappearing. Among these bubbles, microscopic wormholes may appear, but their lifetime is so brief that not even a photon could pass through them. This is the realm of quantum fluctuations, accessible only to theorists. Open wormholes, however, are a different story. Theoretically, they could exist long enough for a signal or even an object to pass through. These are the ones most often discussed in connection with interstellar travel. But their existence would require exotic matter capable of keeping the tunnel throat open. Philosophically, the difference between closed and open wormholes reflects two levels of our relationship to the unknown. Closed wormholes represent a realm of chance and possibilities we cannot control. They remind us that chaos and randomness lurk at the foundation of reality. Open wormholes, by contrast, embody the dream of one day wielding the unknown as a tool to overcome boundaries. Interestingly, the idea of closed wormholes is closely tied to the hypothesis of quantum gravity. If space truly has a foamy structure, then perhaps wormholes are a natural part of it. We cannot use them, but their mere existence might give us clues to the fundamental nature of space-time. Historically, the thought of such microscopic tunnels arose with the development of quantum field theory. Physicists realized that the vacuum is not empty, but an active medium where the strangest processes can occur. The wormhole idea became one of the symbols of this emptiness full of events. Now let us ask ourselves, what if someday we could turn a closed wormhole into an open one? What if future technologies could stabilize these quantum bubbles? It sounds like science fiction, but such fantastic ideas have sometimes become the seeds of new sciences. In the next chapter, we will discuss another fascinating aspect. Could wormholes be used not only for travel through space, but also for journeys in time? We now arrive at one of the most thrilling questions about wormholes. Could they serve not only as pathways through space, but as portals through time? At first glance, this seems unbelievable. Yet a closer look at the equations of general relativity reveals that the possibility cannot be ruled out. The reason lies in the fact that space and time in this theory form a single entity, space-time. Thus, a tunnel connecting different regions of space could also connect different moments of time. The idea of time travel through wormholes was seriously discussed by physicists in the late 20th century. One of the most famous researchers was Kip Thorne. He showed that if the mouths of a wormhole move relative to each other at high speed, or lie in regions of different gravitational strength, a time shift could arise between them. This means that passing through such a tunnel might bring you not only to another place, but to another century. Science fiction has long played with this idea. In novels and films, heroes often use wormholes to leap across time. But when physicists considered it seriously, they found that the equations indeed allow for such scenarios. Yet with them came paradoxes. The greatest of these is the paradox of causality. If one could move into the past, what would stop a person from changing their own history? Could you meet yourself as a child, or prevent events that have already occurred? Such questions undermine the very logic of time. To resolve them, scientists proposed different approaches, from the principle of self-consistency, which forbids alterations of the past, to ideas of multiple universes, where each journey creates a new reality. Philosophically, this conversation is mind-bending. If time is not a rigid line but a web of possible paths, then what does the present mean? Could it be only a node in an immense network of possibilities? And if wormholes allow us to cross these nodes, then perhaps our notion of time requires revision, just as our notion of space once did. Historically, it was precisely the debates about time travel that made wormholes so popular, not only among physicists, but also in mass culture. they became symbols of humanity's dream of conquering fate itself. But science remains cautious. While the equations admit such scenarios, we do not yet know whether they can be realized. Exotic matter, tunnel instability, quantum effects, all are formidable obstacles. In the next chapter, we will look more closely at how physicists attempt to resolve the paradox of causality and what their reflections reveal about the very nature of time. In the previous chapter, we spoke of time travel through wormholes. Now let us turn to one of the sharpest questions tied to this idea. What about the paradox of causality? Imagine you use a wormhole to go back into the past. What if you arrive at a moment before your birth and change events so that you are never born? This is the famous grandfather paradox. The time traveler may prevent their own existence. Such thought experiments show how fragile the very notion of time becomes if treated as a road that can be traveled both forward and backward. Physicists have proposed several ways to resolve this paradox. One is Novikov's self-consistency principle. According to it, any events that occur during time travel are already built into the fabric of history. In other words, you can go back in time, but whatever you do there will not alter the future. It will simply become part of it. In this model, you cannot kill your own grandfather because the very fact of your existence guarantees that it does not happen. Another approach involves the hypothesis of multiple universes. According to this idea, any interference with the past creates a new branch of reality. If you go back in time and change events, you will not erase your original future, but rather end up in a different universe where history unfolds differently. Your home timeline remains intact. This concept removes the paradox while opening the door to an infinite number of worlds. Philosophically, the paradox of causality forces us to reflect. Is time an objective flow, or merely our perception of events? Perhaps past, present, and future all coexist simultaneously, and we move through them like pages in a book. Wormholes then become tools that let us flip through the book backward and forward. Historically, the grandfather paradox and similar ideas have inspired not only scientists, but also writers. Science fiction abounds with stories in which characters face the consequences of their journeys through time. These tales both entertain and provide society with a way to discuss profound philosophical and scientific questions. The scientific approach to these problems remains cautious. Even if the equations permit time travel, the physical realization of such scenarios seems immensely difficult. But raising questions about causality itself helps us better understand the nature of time and the connections between events. In the next chapter, we will turn to another important issue. If wormholes are possible, could they be detected? How might we find evidence of their existence in the real universe? We now come to another key question. If wormholes are possible, how might we detect them? For now, they remain only a hypothesis supported by elegant equations but lacking direct evidence. At first glance, it seems impossible to find a wormhole. It could easily be disguised as a black hole. From the outside, a black hole and the entrance to a wormhole might look identical, a dark region from which nothing emerges. So how could we tell one from the other? Scientists suggest searching for indirect signs. One such sign is unusual dynamics of matter around the object. If a wormhole connects two different regions of space, matter falling into it may behave differently than it would near an ordinary black hole. For instance, one might expect distinctive emission spectra or peculiar oscillations. Another method of detection involves gravitational lensing. Black holes bend the light of stars and galaxies, creating characteristic effects. But if the object were a wormhole with a second exit, light could pass through it and appear in entirely unexpected places in the sky. This would produce unique signatures that might be detectable. Philosophically, this raises an interesting question. Are we even prepared to see what we seek? If telescopes suddenly revealed data that ordinary physics could not explain, would we dare to admit it might be a wormhole? The history of science shows that new discoveries are often met with skepticism. Pulsars were first mistaken for alien signals, and the cosmic microwave background was long dismissed as mere instrumental noise. Historically, serious searches for possible wormholes began only recently, and although no convincing evidence has yet been found, the very fact that such searches are being undertaken speaks to the maturity of science. We have moved beyond seeing wormholes as pure fantasy and begun to look for real observational traces. There are also bolder hypotheses. Some researchers suggest that certain anomalous cosmic events, such as fast radio bursts, might be linked to wormholes. Though highly controversial, the idea itself demonstrates how deeply the subject has penetrated modern astronomy. In the next chapter, we will discuss what possibilities for cosmic travel might open if wormholes truly exist and can be used. So we have seen that wormholes might be detected through indirect signs. But now let us imagine that one day we actually discover a stable wormhole. How would this change the possibilities of space travel? First of all, it would mean the end of the era of slow journeys. Today, even a flight to the nearest star, Proxima Centauri, would take tens of thousands of years with current technology. A wormhole, however, could connect us to that star directly. It would be like building a bridge across the ocean instead of sailing for months. A second possibility would be instant communication between distant parts of the universe. If a tunnel connects remote galaxies, then a signal sent through it would arrive immediately. This would transform not only travel, but communication itself. The universe would become smaller, its scale no longer an obstacle. Philosophically, this would overturn our understanding of space. Today, distance is a fundamental property of reality. We measure it in light years, and it sets the limits of our experience. But if wormholes are real and accessible, then distance ceases to be a barrier. The cosmos becomes one, bound by a network of invisible roads. Historically, we can recall how new routes transformed civilizations. The great geographical discoveries turned Earth from a fragmented world into a global system. Railroads made continents into unified spaces. Aviation linked nations in hours. Wormholes could be the next step, linking galaxies. Yet this brings a new problem. Are we ready for such vast freedom? If the universe suddenly becomes accessible, what will happen to our sense of home, culture, the uniqueness of Earth? Perhaps it is distance and the difficulty of travel that give journeys their meaning. On the scientific side, a key question remains. How could such portals be controlled? If a wormhole connects random points in space, we cannot use it as a reliable route. We would need to learn to manage the entrances and exits. This task today seems like science fiction, but it is precisely what would make wormholes a true tool for humanity. In the next chapter, we will turn to another fascinating subject: how the use of wormholes is tied to questions of energy and what resources would be required to control them. In the previous chapter, we imagined how wormholes might transform space travel. Now it is time to ask, at what cost would such journeys come? For the key issue here is energy. To create or stabilize a wormhole would require resources almost beyond imagination. Calculations suggest that keeping the throat of a wormhole open demands negative energy in colossal amounts. To put it in perspective, the energy needed to stabilize a tunnel large enough for a spacecraft could be enough to vaporize a planet. We are dealing with scales far beyond anything humanity can currently access. Yet despite this, physicists continue to explore hypothetical scenarios. Some suggest that in the future a civilization might harness the energy of black holes or even the vacuum itself to power such portals. Others speculate about more exotic sources such as hypothetical dark energy, which already possesses strange properties of its own. Philosophically, this brings us to a question about the price of progress. Should we open roads to the stars if doing so requires controlling forces capable of destroying entire worlds? Perhaps the universe itself has built-in safeguards against overly rapid expansion, demanding that civilizations mature over eons before they can wield such resources. Historically, humanity has faced similar dilemmas. When people learned to harness the power of the atom, it brought both light and destruction. Nuclear plants provided electricity to millions of homes, while nuclear bombs threatened global annihilation. Perhaps wormholes will serve a similar role, a test of a civilization's wisdom. Another side of the issue is portal management. Even if we had the energy, how would we direct it so that the entrance and exit connect the desired points of space? This is not merely a technical challenge, but a fundamental problem, requiring new insight into the very structure of the universe. Interestingly, in some scenarios, a wormhole might seek out a stable position in space, much like a river finds its course. This raises the possibility that portals may never be fully controllable, but only caught and used while they last. In the next chapter, we will consider what impact the reality of wormholes could have on our society, culture, and philosophy. Let us now look at the subject of wormholes from another perspective. What would happen to our society and culture if we truly gained access to such portals? Imagine a world where distance is no longer a barrier. In a single second, one could appear in another galaxy, and communication with civilizations on the edge of the universe would be instantaneous. This would transform not only science and technology, but the very fabric of human culture. First, the familiar sense of isolation would vanish. Today we perceive Earth as a unique home, surrounded by incomprehensible distances. But if those distances ceased to be obstacles, our sense of home would change. Humanity would face, for the first time, a situation where homeland might mean not just a planet, but perhaps an entire galaxy. Second, economics would change. If wormholes could instantly transport goods, imagine what interstellar trade would mean. Resources scarce in one world could flow freely from another. Entirely new forms of cooperation and competition would arise. Philosophically, the reality of wormholes would force us to ask, who are we in the cosmos? If our history was once shaped by limitations, what happens when those limitations vanish? Is humanity ready for freedom without boundaries? For the absence of barriers does not always bring harmony. Sometimes it breeds chaos. Historically, parallels can be drawn. The discovery of new continents brought both cultural flourishing and the tragedies of colonization. Perhaps space, too, would bring not only inspiration, but conflict. Wormholes could serve as bridges of friendship or as fields of struggle. Another crucial aspect is spiritual. For many, the thought of touching other worlds would challenge traditional ideas of humanity and the universe. Religions, philosophies, worldviews, all would be compelled to seek new answers to old questions. In the next chapter, we will explore how wormholes have influenced art and literature and why they have become some of the most powerful symbols of human imagination. We are nearing the end of our discussion of wormholes, and it is time to reflect on the place they have taken in human culture, art, and imagination. Wormholes have become one of the most recognizable symbols of science fiction. As early as the mid-20th century, writers began using them as a convenient device that allowed characters to cross vast distances. Arthur C. Clarke, Carl Sagan, and later Hollywood filmmakers turned the wormhole into a kind of magical door, but one grounded in physics. In the film Contact*, Carl Sagan portrayed how an advanced civilization might use wormholes for interstellar travel. In Interstellar*, Kip Thorne served as a scientific consultant to ensure that the wormhole looked as realistic as possible. These images had an enormous influence on public perception of science. Millions first learned of wormholes thanks to art. Philosophically, wormholes symbolize hope and the desire to go beyond the possible. They embody the dream that the barriers of space and time can be overcome. In every story about a wormhole, the question resounds, what if? And it is this very question that drives progress. Interestingly, artistic visions of wormholes often precede science. Writers and directors boldly imagine scenarios that later inspire scientists to search for real solutions. In this sense, imagination itself becomes a laboratory of the future. Historically, one can recall how the ideas of Jules Verne anticipated the arrival of submarines and space rockets. Likewise, today's fiction about wormholes may herald tomorrow's discoveries. Even if we cannot yet create or detect such tunnels, the idea itself shapes the horizon of scientific exploration. But there is also a downside. Sometimes popular depictions mislead, creating an illusion of simplicity. The real physics of wormholes is far more complex and demands caution in interpretation. Yet perhaps it is precisely the balance between rigorous science and bold imagination that makes the subject so captivating. In the next and final chapter, we will attempt to draw conclusions and view wormholes not only as a hypothesis of physics or a symbol of fiction, but as a source of inspiration for humanity. And so we have reached the end of our journey into the world of wormholes. Throughout these chapters, we have traveled from the first ideas of Einstein and Rosen to the boldest fantasies of interstellar and even temporal travel. Now let us look at it all as a whole. Wormholes remain a hypothesis. We have not found a single piece of direct evidence for their existence, but this is precisely what makes them a symbol of human imagination. Where facts are absent, dreams arise, and dreams, as the history of science shows, often form the first step toward discovery. The physics of wormholes teaches us that the very fabric of the universe may be far more complex than we once thought. Space and time are not static stages, but living, dynamic structures filled with possibilities. Even if we never find real wormholes, the very fact that the equations allow them inspires us to look beyond the familiar horizon. Philosophically, the subject raises timeless questions. What are boundaries? Are they real or only our perception? Perhaps every limit is an invitation to seek a way beyond. Wormholes become metaphors for the idea that even the most impassable walls may conceal doors. Historically, they have shown how deeply science and culture intertwine. Writers imagine bold scenarios, physicists seek rigorous proofs, artists create visions. Together they form a space of ideas where new meanings are born. And finally, inspiration. Imagine that humanity one day truly discovers a way to travel through space and time.
that our descendants might instantly reach the stars, communicate with civilizations at the edge of the universe, and open worlds beyond imagination. Even if such a future never comes, the thought of it gives us strength and broadens our horizons.
Thank you for joining me on this journey. May wormholes remain not only a puzzle of physics, but also a reminder that our ability to dream is already a portal leading to new worlds.